question 2a is about something really important, because in many ways this is what organic chemistry is for. It's the idea that you can't always convert one thing into another just in a single step. In real life, organic chemistry is about stringing together a sequence of reactions to bring about a change that you need. And it's one of the things that you have to master in A-level. You know, it's one of the sort of key objectives in A-level is to learn to construct syntheses like this. In real life, they can be huge. You know, they can be 20, 30 steps. In A-level, happily, they're not. You know, they're kind of typically sort of 3 steps, something like this. But in order to do these questions, you have to know the reactions really thoroughly and use your sort of imagination, your creative abilities, if you like, to kind of think of ways in which you could put them together to bring about the change that you want. And you have to try to come up with something that's actually going to work reasonably enough. So in this case, you know, I asked for a sequence of 3. I probably should have set the question a bit more clearly, but 1 or 2 people just did something rather straightforward, which had only 2 steps, which was to say, right, well, these are saturated carbons, so I can put a chlorine on there, just with a bit of chlorine and UV, and then I can hydrolyze that chloroalkane group just with aqueous sodium hydroxide, and there you go, job done. The trouble with that is that it's rubbish as a actual practical proposition because of the low percentage yield in that first step. Okay, because you know, it could substitute not just there but here or there. You're only going to get a relatively modest amount of that product probably, and therefore it's not a great way of doing it. So you have to try to think about complications as well as you know, just thinking of something that looks at first sight like it could work. So a good way to approach it, I think, is to look at this and see, right, 2 OH groups side by side, 2 identical groups side by side. What reaction do we know that can produce that? Well, you don't know one that can directly produce 2 OH groups, but you do know a reaction which could directly produce 2 chlorines or 2 bromines side by side, which is this reaction. Okay, so you know that addition of chlorine to an alkene produces that dichloride with chlorines on adjacent carbons. And if you just sort of saw that connection and thought, oh yeah, that would be great because I can then convert those 2 chlorines into 2 OHs, and then all you have to do is to complete it and say, right, can I make an alkene from an alcohol? And of course the answer is yes. That's the only way you know to make alkenes. So it's about spotting the way in. And as I think the way I would have spotted the way in here was to think, how do I get 2 identical things like that side by side? You can't directly get the 2 OHs, or at least not with reactions that you know, but 2 chlorines, yes you can, and then you know how to convert those. So this would be the middle step, and there's nothing special to coordinate, but it did ask you for an equation for each step, as well as the reagents and conditions. So that's just going to be that plus chlorine will give you that's an addition reaction, so there's no other product. So that's going to be the middle step, and then, so we'll call that step 2. So then we need to put in step 1, which is making the alkene, and step 3, which is hydrolyzing the dihaloalkane. So how do we go from here to there, well, that's dehydration of an alcohol. You can see that again, dehydration can be a problem with percentage yield if it can dehydrate to give different products, but because of the symmetry, it doesn't matter whether it loses the hydrogen there or there, you get the same product in this case. So that's fine. And that's an elimination reaction, so it's not reacting actually with anything as far as the equation's concerned. You just get your alkene plus water. But the conditions are important. You need concentrated sulfuric acid and heat. Concentrated is very important there because it wouldn't be a favourable reaction. It's the fact that the concentrated sulfuric acid is very attracted to water that makes the reaction favourable, so that's important. Okay, so that's step one, dehydration to make the alkene. That opens up the possibility of putting the 2 chlorines on, and then finally all you need to do is to replace those with OHs. Now this hydrolysis reaction is done with aqueous alkali. Don't just put reaction with water down, because although it works, it's very slow. It's not a good practical method. So the reaction is with sodium hydroxide, and the key condition though is that it must be aqueous. So you want sodium hydroxide in the equation, but you must either in the equation or above the arrow specify that it's got to be aqueous, because the reaction won't work otherwise. So we've got the dichloroalkane, and because there are 2 chlorines to react, we're going to need 2 NaOHs in the equation, and that's going to give you substitutions, just nucleophilic substitution, remember. OH minus goes in, Cl minus comes out, so you get your diol being formed, and you're going to get 2 NaCl as your other product. So that's a very simple example of a synthesis problem, and it's something you're going to need to practice a lot, because it's a very good way of making sure you know your reactions. And as I say, it's a taste of what organic chemistry is really all about in the real world, is coming up with reaction sequences like that. Part B is a percentage yield question. It didn't depend on you having a particular route for that, because it just gave you the overall percentage yield for getting from here to there. So it told you that overall the yield there was 78%. So remember, your definition of percentage yield is the actual moles you get in the reaction divided by theoretically what you should have got based on the equation that's written down times 100. So in this question, you know what the actual moles are that you need to get, because that's the premise of the question, that you need to get 1 kilogram of this product. So you can convert that into moles, and that tells you your actual moles, and you know what the percentage yield is. So what you can calculate is the theoretical moles, and the question is that useful? And the answer, of course, is yes, because theoretical moles means how many moles would you get if what happened in the equation is all that happened, if there weren't any losses due to other things like other reactions happening. And of course, theoretically, each mole of that should end up as a mole of that, because although there are 3 reactions, each time 1 mole of this goes to 1 mole of that, goes to 1 mole of that, goes to 1 mole of that. So that's what theoretical moles means, and it therefore is equal to the number of moles of starting material that you need, because theoretically each of those moles should give you a mole of that. So that's the key, is to realise that what you have to do is solve for the theoretical moles, because theoretical moles is equal to the moles of starting material. So you do the rearrangement first. Remember to rearrange the equation before you put any numbers in there. So theoretical moles slides diagonally up here, percentage yield slides diagonally down there, and you get theoretical moles is equal to actual moles divided by percentage yield times 100. Once you get to that stage, it's just a number crunching exercise. That was the crucial bit, is making sure you understand what actual moles and theoretical moles mean in the context of this question. So actual moles, we can get that because we need a mass of 1 kilogram of this, and so we get moles is mass over mR, which is 1,000 grams, because we always work in grams when we do moles, divided by 102, which is the mR of this, gives you 9.804 moles. Okay, so that's our actual moles. So we can plug that number into here. Theoretical moles is 9.8 over 4 over 78, which is the yield times 100, and that comes to 12.6 moles is the theoretical yield. And as we say, that's equal to the moles of cyclopentanol needed. So then all we have to do is turn that into a mass. So moles times mR, which is 12.6 times 86 is the mR of that compound, and that comes to 1084 grams. And you could leave it as that, but we should probably round it down to two significant figures, really, because we were only given the percentage yield to two figures, so 78%, and you can put it back into kilograms if you want. So that's 1,100 grams, or 1.1 kilograms, to two significant figures. Part C wants to know what happens to this if we react with excess aqueous acidic potassium dichromate. So notice a couple of things there. First of all, as we've mentioned before, the whole package, aqueous acidic potassium dichromate, not just potassium dichromate. Nothing would happen just with potassium dichromate. It's got to be aqueous, it's got to be acidic. And secondly, notice the word excess. When you see excess in a question like that, it usually is a clue that says it means that more than one functional group is going to react, and excess is saying there's enough of the reagent to make sure that all of the functional groups can react. So obviously the point here is that you've got two secondary alcohol groups, and secondary alcohols can be oxidized by aqueous acidic dichromate, and the fact that there's excess means there's enough for both of those secondary alcohol groups to oxidize. And what they oxidize to, of course, are ketone groups. So you get a dione, which looks like that. Okay, so secondary alcohol oxidizes to ketone with aqueous acidic potassium dichromate. Now I asked you for an equation, and you have to remember the convention, which is that in these organic oxidations you don't bother writing in the oxidizing agent explicitly, because that gives you messy, complicated equations, and if you're only really interested in the organic part of it, it's just pointless. So what we do is use this trick of using a magic oxygen to represent the oxidizing agent. So it just balances into your equation as an oxygen atom. And because we've got two secondary alcohol groups, we're going to need two magic oxygens, one for each of them to oxidize it to the ketone. And remember what happens to get from there to there. What you have to do for each group is take two hydrogens away, one from there and one from there, so that you get two hydrogens combined with an oxygen to make the water, and you get a double bond here. The same thing here, so that's going to give you four hydrogens altogether, plus the two oxygens, gives you two waters to balance your equation. So that's what's going to happen. And we've already said these two groups that are here are called ketone groups. So that was the answer to the second bit. Not just carbonyl. Carbonyl means C double bond O, so that's not wrong, but it's not enough. The reason you don't just call it a functional group carbonyl is because C double bond O behaves very differently if it's in a ketone compared to, say, when it's in a carboxylic acid. To some extent different again from when it's in an aldehyde, and you're going to meet a whole bunch of other groups that include carbonyl as well. So when it asks for the functional group, you have to give the context. So the word is ketone there. And the other thing is, if it says name, it means name. You can't just write C double bond O. That's not a name. So ketone was the answer to the second part.